in our last class? Can you just recall?
I think we did impulse and then Newton's third law of motion also we did. Yes, ma'am, we started with
Mm-hmm.
Newton's third law of motion.
Third law,
Yes.
correct? Yeah, there is no much mathematics involved in it, but it is actually one important rule. Like action and reactions are equal and opposite. But there are some misconception, like just by using the word action and reaction.
Yes.
So it's like we say, like if I apply a force, it is not that it give me a reaction. It's both are force only. Okay, if I apply a force on something, I'll get a reaction, and it's like instant reaction. It's not like after some time. Okay, yeah,
Yes.
and it's like, you know, it's not like cause and effect kind of a thing. It's like I apply a force and there is reaction. That's all. Okay, and both are force. Okay, it's not like action is also a force, reaction is also a force. Just because, you know, I'm like, action is something we are applying a force, reaction is like from the other body what we get in response to that is reaction. Okay,
Yes.
so that is one thing. And yeah, like this third law plays a very important role in explaining many things. Later you'll come to know when we take up some problems in this particular chapter. And yeah, with the second law, like maybe we had done little, you know, we spent some time with discussing its mathematical form and stuff like that, and we have defined something called as momentum as well. So your second law states that the force is directly proportional to the rate of change of momentum, dp by dt. That is one important relation, because now we'll be just going ahead with the concept of conservation. Okay, like here maybe the first time you're coming across conservation principle. Like in the early school, have you ever heard like conservation of some physical quantity?
Not really.
Huh?
It started in this chapter.
Okay, you never heard about some conservation principle, right?
No.
Yeah. So have you heard some statement like energy can never be created nor be destroyed, but it can be converted? That is also a conservation principle. See, for a closed system, okay, yeah, like we are not allowing some energy to escape or some mass to escape like that. You know, the total energy of the system is conserved, means constant. Conserved means in physics it is constant. Okay, so the point is what we are trying to convey is like for a closed system the energy is constant, means the total sum remains constant, but the internally, like one form of energy can convert into other form, that is allowed. Like maybe some kinetic energy can convert into potential energy, or potential energy can be converted into kinetic energy, or some, you know, heat energy, like different forms of energy you can take. Okay, electrical energy, thermal energy, whatever may be the type of energy, like the total energy remains constant, but it can convert from one form to other form. You can never destroy energy. Okay,
Yes.
it's simple like mass conservation. What do you mean by mass conservation? Again, same. Like the total mass of a system is constant. Okay, the total mass of a system is constant, which mean to say, I mean, with mass we have no other option also. I cannot convert as of now. Like I can further fragment it. Like I may had a 10 kg mass. I will cut into pieces. Okay. But when I, like maybe like I cut into some 3 pieces. Like if I now measure the mass of each blocks, the total sum must be 10. Maybe like 6 plus 3 plus 1 still sums to 10. It can never be 11. Correct?
Yes.
Yeah. Or it can never be 9. It will be constant. Okay. Is that clear?
Yes. Yes.
Yeah. So now, I mean, right now we assume energy and mass are separately conservable, but actually at later point of time you will come to know, like it, like your total energy conservation and mass conservation separately will not work out. Actually, you should include both together. That is your Einstein's equation, E equals to mc square. Correct? Like you can convert mass into energy or energy into mass. That is possible. Okay, if that is valid, then I can never say conservation of energy separately holds good and conservation of mass separately holds good. but togetherly energy and mass conservation will hold good. That happens at very high energy part of physics. In our normal, whatever till now you have discussed, or maybe few things like in Newtonian mechanics, Galilean mechanics, and all, your mass separately conserved, energy separately conserved. But with the nuclear physics, like high energy physics, okay, where the energy involved is very high, there definitely energy and mass togetherly conserved, but not separate. Okay.
Yes.
Yeah. Coming back to the concept in this particular chapter, so I'll just share my screen. Just a minute. Just give me a minute. Loss of motion. Yeah. Can you see the screen?
Ma'am, it's loaded.
Yeah.
In the textbook, right?
Yeah.
Yeah, I can see.
Okay. Yeah, I think we have discussed till here.
Yes.
So here what we are saying is, yeah, that's all. There is no cause and effect relation implied in third law. The force on A by B and the force on B by A act at the same time. That is one point you should understand. And going ahead, so we have is like action and reaction. This is very important. Action and reaction forces act on different bodies, not on the same body. This is important. Okay, when we do some problems in next, this factor is very important. Like, what is FAB here? This is the force on A. Let me say some object is here, and there's one more object is here. Let us say somebody pushes it, so it hits on this object. Okay, let me say this is A and this is B. Okay.
Yes, ma'am.
Yeah. So the point is, FAB is the force on A, like it is on A because of by B. Okay. But what is the FBA? FBA is the force on B due to the hitting effect from A. Okay.
Ma'am, why is it negative?
The directions are opposite to each other.
Oh, okay.
Force on A, see, force on A by B will be in this direction. It hits in, it tries to push in this direction, correct?
Yes.
Your FAB is this way. Now what is FBA? FBA is force on B by A. That means it tries to push in this way. Correct?
Yes, ma'am.
Both are acting in the opposite direction. So we put a minus sign. Their magnitudes are same. FAB equals to FBA. But their directions are opposite. Like when you write in vector form, you get a negative sign. Okay?
Okay.
Yeah. And it is like force always occurs in pair. Okay? That's like how to say, like your action and reaction both are force, and always it is easy to say force occurs in pairs. You don't think like action is something different, reaction is something different. Don't take like that. It is better to say any force always comes in a pair. Okay. So that is one important factor here. Yeah. So going ahead, there's some sound coming. What it is?
It's the fan sound.
Huh?
Is it the fan sound? Because there's no other sound.
I don't think so. Let's see. Yeah. Now, this problem, we'll just talk about it. But yeah, first I'll take up conservation principle, then I'll come for this. Okay. So conservation of momentum. So what do you mean by conservation? Just now I told, yeah, it's nothing but something remains constant. Conservation means constant. What is constant here? Momentum is remaining constant. Okay. What is remaining constant? Momentum is remaining constant. For that, I mean, in physics, your conservation, many conservation laws are there, like energy, mass energy, equivalence. And then now we are talking about just momentum. When we come to chapter number 6, we talk about one more quantity called as angular momentum. So many conservation laws are there, which are very important. So we'll start from considering Newton's second law. Okay. So what we'll do, we'll consider Newton's second law. So in Newton's second law, what we have, it's like force is equals to rate of change of momentum. I'll write by taking constant as 1. Can I able to write like this?
Yes.
Yeah. So now I'll use a word called as isolated system. Isolated system. Okay. Which is like net force on the system is 0. Net force on the system is 0. Okay. So what do you mean by net force? It is like there is a object here. You apply a force in this direction. I apply some force equal and opposite to it. So the net force is 0. So such a situation. Or maybe no force acting. That is also a trivial case. Okay. A trivial case is no force is acting. But net force acting 0 means it doesn't mean that there are no force at all. It means that there are forces, but they are balanced. Okay. So then what you can able to write, if F net equals to 0. And more precisely, it is about external force I'm talking. Okay. So now what you will get, dP.
0, right?
Yeah, that is true. But now we are looking in a different way. So what I can do, dP by dt equal to 0, I can do. Correct? Now, we will use our knowledge of mathematics. When can be the differentiation of constant function is 0? D by dt of some constant if you have, that only becomes 0. So I can say my momentum is constant. So when do we say momentum is constant? If the net external force acting on the system is 0, it is better to say external also. Because internal force anyway comes in pair. So obviously they get cancelled out. Okay. So net external force acting on the system is 0. Then the momentum is a conserved quantity. So this particular case is called as conservation of momentum. Okay. Conservation of momentum. Is that clear? So, or you can write the product of mass into velocity is constant. And now you can see like what you told, no? most of the case our mass is constant. And if the product of mass and velocity should be constant, means velocity should remain same. That means A should be 0.
Okay.
Okay. So that's how you can
scroll up a little. I wanted to copy it.
Yeah. From here.
Yes, ma'am.
So in NCERT they are doing it in some different method. I'll just share and I'll tell what they are doing. Okay. Like they are taking an example and doing. Okay, that is in 5.7 they're talking about a gun and the bullet system. Okay, so it's like, let us imagine the there is some gun. So this is our system and inside it there is a bullet. Okay, so let us say gun and bullet, and when you fire the gun, like the bullet will come out and it moves with some velocity v. Correct?
Yes, ma'am.
Yeah, I mean, this is given in a different way, but your question will come in a different way. So that also I'll discuss later. So now what do you observe? Like the bullet is going in this direction. Okay. And yeah, like, your conservation of momentum is actually the consequence of first law and Newton's second law and third law. Okay. So that is how they are coming to this point. So see here, let us say the force on the bullet by the gun. Okay, like when you just trigger it, the force on bullet by gun be something like F. Okay. Now the force on gun by bullet will be how much? It will be minus F.
Minus F.
Correct? If that was F, this will be minus F. Correct? That is from Newton's third law I'm writing. Correct?
Yes.
Because this is my total system is this, like entire bullet and gun system. After firing also you should see what happens to how the gun moves and how the bullet moves. Like you should consider your entire system as gun, gun plus bullet. Because I'm looking from outside, for me this entire thing is one system. Okay. Yes. Defining system is in your hand, which is my system, like which is my particle I'm observing. That is in my hand, and in our most of problem we choose that as system where complications are less. Okay. Choosing gun and bullet as an entire system is easy. Okay.
Oh.
If you deal with like gun as separate system, bullet as separate system, solving problem becomes very difficult. Because I don't know any detailation about gun and bullet separately. But I know like as a together, I know it in a better way. Okay. So that's how we consider. Okay. And now if I consider over some time interval delta t, over a time interval delta t, okay, over a time interval delta t, we know that just now we said like action and reaction both applies on the same time. If that is true, how much F into delta t is there? That should be equal to minus F into delta t. Correct?
Yes.
Yeah. So magnitudinally both must be same.
Yes.
Yeah. So now what is this F into delta t? F into delta t, if I consider the product, this is nothing but some momentum, change in momentum, sorry. Correct? F into delta t is nothing but change in momentum. So what it is the momentum of the change in momentum of bullet. So I'll write it as PB.
Okay.
Okay.
Yes.
And then what is minus F into delta t? That is similarly change in momentum. This was for bullet.
Bullet.
And this was for gun.
Yes.
So which is PG I can write.
Yes.
Correct? And we can say if initially, okay, like before firing, both are at rest, no? The bullet was sitting here and the gun was also there. So both are at rest. Correct?
Yes, ma'am.
Yeah. If, both the system were, if the system was at rest, the change in momentum, should be equal to the final momentum. Okay, change in momentum, if I write, change in momentum will be like, P final minus P initial, no? So which is nothing but P final minus 0, which is nothing but final momentum, correct? I can say this now. If initial momentum is 0, change in momentum must be equal to final momentum. Do you agree?
Yes, ma'am.
Yeah, so this is one fact. And now, what happens is that we can say my final momentum, that is PB, must be equal to minus PG. Can I say that? From looking into these two equations as well?
Yes, ma'am.
One is F into delta T, one is minus F into delta T. Say nothing but PB equals to minus PG, or you can say your like vector notation. This is okay. My PB vector plus PG vector must be equal to 0. This is nothing but change in momentum I'm talking. Okay.
Yes.
So now change in momentum is nothing but equal to final momentum. That is also true. So your final momentum sum is 0. Do you agree?
Yes, ma'am.
Yeah. The total sum of final momentum is also 0. And how much was initial momentum? That was also 0. Now what we are getting, whatever the total momentum was there, the final momentum is also same.
0.
Yeah. It doesn't mean that the bullet is not moving. The total final momentum of the system is 0, which means like if the bullet fires in this way, your gun will recoil in the opposite direction, which is equals to, yeah. So if the mass of the bullet be small m, mass of the gun be capital M, if this moves with a value like m into v, your gun will recoil with a value which is equal and opposite to it. So I can say minus mv.
Yes.
Yeah. So it recoils with a value of minus mv, but later we can get like, I can try to write it in terms of capital M as well. Okay. So that is how, if you fire a bullet in forward direction, the gun will recoil. That's what we usually observe, because like bullet will carry so much of velocity. Like usually with the firing, it carries large velocity, right? That's how it can go for farther distances, or no?
Yes, ma'am.
Yeah. Yeah. And but we don't see much recoiling of gun. We don't see gun is going back with a farther distance. Why don't we see like that? It's because your mass of the gun is so large when compared to the mass of the bullet. Do you agree?
Yes.
Yeah. And that means the velocity with which the gun recoils will be lesser. Correct? I can say my momentum of gun must be equal to the momentum of bullet, magnitudinal wise, equal and opposite. Like when you talk about direction, it should be equal and opposite. Okay. Or you can put a minus sign, which tells you it is in the opposite direction. No problem with that. Or your velocity is like m by capital M times of v. Correct?
Yes.
M by capital M. Like M is very small. Bullet is not of kg together weight, no? Some grams will be there. And gun is like quite heavy when compared to this. Some grams by some half a kg you will be doing maybe. May not be half a kg, just I'm taking randomly. But like some small value by large value, right?
Yes.
Clearly you can tell your capital V will be smaller than small v. Do you agree? So this can also be called as recoil velocity. You didn't get what I said?
Ma'am, can you just explain this bit once more?
I said, like, I'm just taking some value. I'll say M as 10, okay? And capital M as like 100. This is V, okay? So this is my capital V. So 10 by 100 is how much? 0.1.
1
This will be definitely less than 1.
Yes, ma'am.
Your capital V will be some number which is multiplied by some less than number 1.
Yes,
Like
ma'am.
0.1 into V will be less than, like if V is 10 now, 10 meter per second, capital V will become what? 0.1 into 10, which means 1 only.
Yes.
Smaller than 10, correct?
Okay, so capital V will be smaller.
Capital V will be smaller. Like it's a just ratio checking. Okay,
Yeah.
you are dividing a smaller number by a bigger number. So obviously that will be lesser than 1. And you are multiplying that with the velocity of the bullet. So obviously it will become less than that velocity, correct? It's a math.
Yes.
Understood? So your gun will recoil with some smaller velocity, and that's why usually people will tell like don't hold it close to your face when you are firing. Okay, like slight recoiling will be there. It may hurt your face. Okay, so you should hold it little, like there is a proper position near the shoulder and all, and you should allow it freely to recoil. You should not to hold very tightly, or else your shoulder will get hurt. Okay, so that you should allow it very smoothly to recoil. If you hold it tightly, like all the recoiling you're taking on your body. And in that case, it's like, your like the mass of the gun plus mass of yourself, like mass of the person will be added. Like it may recoil with lesser speed, but it hurts you. Okay, so that's how it is. Okay, understood? So usually in exam they may ask you as a problem like recoiling velocity of the bullet. So you can just consider the simplest case. Okay. You can say with the taking gun and bullet as a system, once the bullet is being fired, like it's an isolated system because there is no external force acting on it, right? There is no one to push the gun, right? It is just triggered and then it just moves away, correct? There is no external force acting on it, so that it's a case for like momentum will be conserved, correct? Momentum will be conserved. Initial momentum is 0. I'll just write the equation if you want. Like initial momentum is 0. So final momentum, like net momentum, must be 0. But final momentum is consisting of 2 parts. That is momentum of the bullet plus momentum of the gun must be 0. Correct? Which you can tell momentum of the gun will be equivalent opposite to momentum of the bullet. But momentum is nothing but product of mass into velocity. Obviously, mass can never be negative. So your velocity should be in the like opposite direction. That's how it is. Okay. Understood the concept of recoiling?
Yes, ma'am.
Yeah. So you can say conservation of momentum is true in the case of bullet and gun system. Like they can frame in any way. Okay, they may ask you assuming conservation principle, get the expression for recoiling velocity, or they may say is the momentum is conserved in the case of bullet and gun system. They can ask in any way. Correspondingly, you just need to write this, okay, with a minimum explanation. Okay. And conservation of momentum is like effect, like it's the consequence of Newton's second law, because we are considering force as m into, rate of change of momentum, and it is also consequence of Newton's third law, equivalent, opposite, action and reaction part case. Okay. Then only I can write this. No, I can write this equation only by assuming Newton's third law, or like this particular thing, Fn minus F. Okay.
Yes.
Understood? Yeah, they have discussed in this when your NCERT 5.7. Yeah, they are going in an indirect way of saying, no, if initial momentum was 0, final net momentum is also 0, which means it is constant or conserved in the case of F external 0. Okay. Yeah. So now if there is some initial momentum, like in general, we'll write in general, okay, if initial momentum be PA and final momentum be PB. Okay. 1 minute. Okay, this, Yeah, I will not discuss about this because what they are discussing, no, that will anyway come in detail in chapter 6. We'll discuss there. Let us not just confuse too much. I'll give you just example. I'm not going to write down the equation. I'll give you an example. Okay. So what they are saying is, you have one object, another object is there. It comes and hits it. Okay. Like initially they had some initial momentum, both. Like sum of momentum of A plus momentum of B. Okay. Yeah. Like it is just moving with uniform velocity. There is no acceleration. That means F external 0. Correct, no? External force can be 0, but still velocity can exist, no? Acceleration is the only one which is 0. But velocity is constant until they collide, correct?
Yes.
Yeah. After hitting, now it's like it can go, move in one direction, the other can move in other direction. Correct?
Yes.
But if you allow the collision to happen in some kind of a column, okay, so then you are restricting its motion. Both will still move in the same direction. Okay, that is no collision in 1D, collision in 2D. That's all. Okay. So finally they attain some momentum, P final. So you should apply initial momentum must be equal to final momentum. Anyway, the mass is not changing. If it has velocity like initial velocity, I'll say like U1, U2. This will have some velocity like V1, V2. So their conservation terms, you can set it up. Like MA U1 plus MB U2 must be equal to MA V1 plus MB V2. Okay. Like this total thing is initial momentum, no? Yes. Initial velocity, initial mass. This total thing is final momentum, no?
Yes.
Yeah. And provided I have just taken in one direction. 2 direction means what you should do? Can you guess? Two direction means momentum is a vector quantity. Momentum along x direction should conserve separately. Momentum along y direction should conserve separately. Okay. You should write 2 equation there. Velocity, no, which is a vector quantity. Only one direction conservation is there.
So then x and y. Okay.
You have to write like everywhere you should write x suffix like ux, ux, here vx, vx. Then you have to write one more for y, 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 y. But the net momentum is conserved. Like, when they scatter in 2 direction, okay, like they scatter in such a way, your momentum along this and this should be equal to this net sum. Their y component should cancel. Only you should get x component. That's how they split. Okay.
Yes.
Anyway, don't worry too much about it. Anyway, we have a detailed discussion in that chapter 6. Okay. Yeah. Hope this is still here. It is clear.
Yes.
So now, which one we will take up? Yeah, equilibrium of particle is there. So I'll just take that also. What do you mean by equilibrium of force or equilibrium of a particle?
A net external force becomes 0.
Yeah. Equilibrium of a particle means it's so simple. Net force must be 0. Correct?
Yes.
If there is a particle, just a general discussion is there, like F1 and F2. When it can be in equilibrium, so if they are in the vector form, I should write my F1 vector plus F2 vector should be equal to 0, or your F1 should be equal to minus F2. Correct? Yes or no?
Yes, ma'am.
Yeah. Now, if there are 3 forces acting, okay,
3.
Example with 3 forces, still they can be 0, no? How can it be? Like, I have my F1 here. This is a particle. And there is F2 here. Okay. Now, where will be the resultant of these two? Somewhere in between it will come. I'll call it as F12. Somewhere in between. It need not to be exactly the midway. It depends on whether F1 is greater or F2 is greater. Correct? That you can use your tan theta formula. Tan theta is equals to B sin theta by A plus B cos theta. Correct? Yeah. So now I can have my third force. Yeah. Which is exactly opposite, equivalent opposite to your F12. Then you can say your system is in equilibrium. If your F12 is equivalent opposite to F3, then the system will be in equilibrium. So, yeah, if the system has to be in equilibrium, minimum two forces are necessary. If one force is there, no possibility of equilibrium, no? Unless it is a zero. Correct?
Yes.
So, equilibrium means two force or more than two force. Any number of forces can act. And like one force should balance all other force. That's how you can visualize. Correct?
No.
Any doubt?
No.
And also when I say this, my x component, y component should be, like if I had to say in the vector notation, if I write F1 vector plus F2 vector plus F3 vector should be 0. Correct?
Yes.
The total sum of all the vector sum of all the forces should be 0. Yes or no?
Yes.
Which means now it should be valid along all the x, y and z direction. So that is F1x plus F2x plus F3x
Equals to 0.
should be 0. Okay.
Yes.
And similarly, their component along y, F1y, F2y, F3y is 0. F1z, F2z, F3z is equals to 0. Okay?
Yes.
So that's how, you can check for equilibrium of a particle. Okay?
Yes.
Yeah. So here is one problem which will take out that type of such type of problems can be there. Hope you can see that example 5.6.
Yes, ma'am.
Yeah. Do you want me to share that screen or shall I just continue with this slide? So see, example 5.6. There's a diagram given to you. There's a mass of 6 kg is suspended by a rope of length 2 meters from the ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope as shown. What is the angle the rope makes with the vertical in equilibrium? Okay. So like you need to find out in equilibrium case, what is that angle that makes with a vertical direction? Okay.
Okay.
So that means, so I'll just take up that diagram. So you have overall 2 meters is there, but force is applied in the midpoint of the rope. That means like somewhere at 1 meter you are applying a force and the mass is still downward. So which is like vertically downward you have the mass, which is of 6 kg. Correct?
Yes.
Definitely this is something like this. Correct?
Yes.
So what is the angle that is made with the vertical? So this is where you actually now onward see the importance of resolving of the vectors. Because if I had to see equilibrium case, I should make net fx along 0 net Fy 0, net Fz 0. Like I should resolve along XYZ direction. And anyway, here all the problems are in 2 dimension. You can ignore Z direction. Okay. So here you have a 50 Newton force. Now 6 kg is mass. So what will be the force acting? That is M into G, no?
Yes, ma'am.
There is
So
6
if
into
B
10 we
is
can
equal
take.
to 10, right? So 16 Newton.
Yeah. Yeah. 60 Newton will be acting downward. Now there is some term like T is written. Do you know what is this T here? Don't know? So like T1, T2, that's what they had written, yes?
Okay.
Correct, no?
T1.
So, see, I'll tell you what it is. So this is T1 and this will be actually T2. But here also you will have T2. Okay. See, you imagine something. There is a string or thin, thread kind of a thing, and it is, you are attached some mass to it. You are attaching some mass to it. There will be some weight acting downward. Do you agree?
Yes.
So now, but because of its weight, the object is not falling down, correct? There must be some force which is balancing this downward force. Do you agree?
Yes, ma'am.
That is what we call it as tension. Tension in this string. Okay?
Yes, ma'am.
Understood?
Yes, ma'am.
So now it will balance like tension is equals to M into G in the simplest case. Or else this, because of this is some kind of unbalanced force, it should just definitely goes down. Someone should hold it, right? Or else it should not leave. Correct?
Yes, ma'am.
But this tension is dependent on which material or which wire, this is made up of. What material it is made up of. Okay. Sometimes if you just use some cotton thread kind of a thing, it can just withstand some small masses. Now you think like you take some steel thin. Okay. I mean, the string made with some steel or some metal wire, they may have some larger capacity. Correct? Like,
yes.
This exactly becomes the material property which you study in detail in elasticity. Okay, but there is some maximum tension, no? Beyond that, it can, like I keep on adding some mass to it, like 100 kg I put, then this wire may break. There is a maximum limit which it can withstand, but at the equilibrium case, I can clearly say tension equals to M into G. Okay.
Yes.
Yeah. The other thing is, as long as you see only one string, the tension will be same. Okay. Then tension in the same string means same tension throughout.
Yes.
With NCERT, I think with only 1 or 2 string they will do. Okay. Same string, same tension. Like throughout from here to here, it is same tension. Okay. So now, but at this point, I just have made, I have pulled it. So now the tension will not remain same. Some kind of pulling, plucking, fixing, clamping, tension will change. Okay. So here one tension, from here to here one tension, from here to here one tension. Okay. And how to draw the direction of the tension. Like for example, if you have a string here, which is rigidly clamped here. Okay. And some mass is attached here. Okay. And you imagine like you are pulling with some force F. Now the tension direction will be like you had to observe from which mass you are observing. Like my mass is here. I look back because my string is in the opposite direction. So away from the mass you have to draw. Okay. Away from the mass. It is always like a kind of pulling force. It tries to pull the mass because you are also pulling. It tries to oppose that. It's like that.
Yes.
Okay. So the same logic I have applied here. Like there is a weight which is acting downward. Tension, like I want to see what is the tension which is acting in this direction. So you observe from this point and draw a force which is opposite to it. Correct? So that is how you get like this way. Okay, it tries to pull the object.
Yes.
Now if if there is a rigid clamping here, I try to see what is the tension here. So now it is like already you can apply your logic of Newton's third law. So if this is pulling in this way, there must be equal and opposite reaction. Then you must see a tension which is opposite to it at the rigid clamping point.
Yes.
So that is why, I am looking from this point. Now my string is this way. So it tries to pull in this direction. Correct? Pulling force. Tension is a pulling force. You can remember like that. Okay?
Yes.
Any doubt?
No.
Clear? So because maybe n number of problems will be framed usually, but in NCERT that much of discussion is not there on the tension forces. So this is how it comes. Okay, your tension force is because of the electromagnetic origin, like elastic property or electromagnetic origin. Because we know in nature only 4 forces are there. No, I cannot say tension is something new force, but the tension is because of electromagnetic origin. Okay. But it tries to balance here, in this case, the gravitational pull.
Yes.
Yeah. So now it is simple. And I think you agree, like from here to here, one tension T1, from here to here, one tension T2. Okay. So if you observe from this point, my tension is away. If I observe from this point, my tension is like T1 here. If I observe from this point, my tension is T2 here. If I observe from this point, my tension is T2 downward. Okay. Now it is very important which you define as your system. So now what I will do is I'll look into only 6 kg mass here. Okay. So what are all the forces acting on 6 kg? So I'll just draw that. I could see one mg acting downward. And there is a force 10 to T2 is acting upward. Do you agree?
Yes, ma'am.
Now, can I call this direction as y-axis?
Yes,
Can I call? And this horizontal direction as x-axis? Just to give you that idea of, we are talking, we are making Fy0, summation of vector sum of Fy0. Correct?
Yes, ma'am.
Which means we assume upward direction as positive, downward direction as negative. This I already told you with the vector notation.
Yes, ma'am.
So I can say T2 positive minus mg should be 0.
Yes, ma'am.
Net force, no? Like there are 2 forces, and I can say my T2 is equals to mg. Okay? T2 is equals to mg. Like you can even apply like upward force equals to downward force. I have no problem. UF is equals to DF. When you are applying like that, you no need to worry about plus and minus. All net upward must be equal to net downward. Okay? Or like summation over Fi equals to 0. Equilibrium means you do like this. Non-equilibrium means you replace 0 by m into a. That's all. Okay? Yeah. So now coming to other point, because our job is not just to find out theta. I want theta. Now what we'll do, we'll consider at this point. Okay. So we have one force like, 50 Newton. I'll consider this now. That point I'll consider, that plucking point. What we have T2 acting downward. We have 50 Newton in this direction. And something like T1 in this direction, correct?
Yes, ma'am.
So now how can we resolve? So now this is making some angle theta. Correct? See, with T2 and 50 Newton, I have no problem. Because it is acting along X, this is acting along Y. But this is making it some general angle. So we'll make it, or we'll resolve it into X and Y direction. Okay. Y direction is how much? T1 cos theta I'll write. Do you agree?
Yes, ma'am.
This is the component of the vector where theta is attached. The other component will come here, which is T1 sin theta. Correct?
Yes, ma'am.
So now I can balance. My T1 cos theta must be equal to T2. Can I write like that?
Yes, ma'am.
T1 cos theta, like upward force equals to downward force, or still you can do T1 cos theta minus T2 equals to 0. Then you can do T1 cos theta equals to T2. That's your choice. Hope you got this step. Correct?
Yes, ma'am.
And similarly, what I can do, I can apply as the system is in equilibrium, summation over fx equals to 0. Also I can do, I can say like 50 Newton, I'll take it as positive. Correct? This direction as positive, this direction as negative. So 50 minus T1 sin theta is equals to 0. Can I able to write like that?
Yes, ma'am.
Or you can write T1 sin theta equals to 50. Correct? Like left side force equals to right side force. That's what. Correct now? I'm
Yes.
balancing left side force equals to right side force. T sin theta equals to 50. Correct?
Yes,
So you
ma'am.
can call this as equation 1. You can call this as equation 2. Now T2 value we know already, M into G. Correct? But we don't know what is T1. What we will do is, because we want theta, they are not asking you T1. That can also be found out later by substituting theta. So what we will do is, we'll do 2 by 1. Equation 2 divided by equation 1.
So 5.
Okay. T1 will go away. Sin theta by cos theta will give you tan theta is equals to 50.
50 by
0. Correct, no? 50 by 0 is there, no? Sorry. 1 minute. Did we go wrong somewhere? Just a minute. Ah, 50 divided by T2 will come, no? Sorry. 2 by 1 I am doing. 50 divided by T2, correct? Correct, no?
Yes, ma'am.
50
So 50
divided by
60.
T2. So 50 by mg, no?
Yes.
What is the value of m into g? 60, na?
60.
I can directly write 5 by 6.
So tan will be 5 by 6.
Tan theta is 5 by 6. So theta will be
5 by 6.
tan inverse of 5 by 6.
We
Okay.
don't have to write the degree.
No, you can get it. But this is a standard triangle. 5 by 6 will give you 40 degree actually.
Okay.
Okay, this is one standard triangle. But you can refer your table, no? You had that?
Yes.
You can check there. 5 by 6 means something less than 1. Like how much it will be? Like 0.7 something it will be. Something
Yes.
greater than 0.7 or 0.8. Yeah, it will 0.8. Like 50 by 6 kind of a thing you can imagine. So 6 8s are 48. Okay.
0.8.
Slightly greater than 0.8. So you can check, this is a standard angle with 40 degree. Okay.
Okay.
If you have table, you can check. Is that is nearby you?
I'll just open it.
Yeah. Like 39 point something will come. Check directly at 40 degree. What is there?
40 degree is 0.8391.
Yeah, this will actually comes out to be 0.8333 something. 39 point last. 39 is how much given?
39 is 0.8098.
So better is this one only, because there is this will be almost like 39 point, 50 minutes something will come. So like, but you are already given with the table of 10, 20, no? So just go up with 40 degrees. Okay. Understood? So now if someone asks you what is the tension T1, what you will do? Substitute here. Okay. So T1 is equals to, you can here you can substitute. This is better. T1 into sine 40 degree is equals to 50. How much is sine 40? Can you look and tell me?
Sine 40.
Yeah.
Sine 40 is 0.6428.
0.6428. Okay, let it be just 0.64, or you can write one more decimal. So this will give you 50 divided by 0.64. Yeah, something around 78 you will get. Okay. Yeah.
Yes.
Understood? Any doubt?
No.